Welcome to part 7 of the IAS Edexcel Chemistry Unit 1. Uh, Today we'll be looking at covalent bonding. So let's just get on with it really quickly. 3.1. Understand that covalent bonding is strong electrostatic forces of attraction between two nuclei and the shared pair of electrons that pair them up based on the evidence. Okay. The two evidences are the physical properties of giant atomic structures and electron density maps for a single molecule. Okay, so what do we mean by covalent bonding? Let me increase the size of this. Covalent bonding is essentially electrostatic forces of attraction between the shared nuclei, the shared electron, sorry, and the positive nuclei. Okay, so this nuclei are positive, and in the middle there are electrons which have a negative charge. Negative charge and the positive will attract each other, hence this is known as covalent bonding. It's that electrostatic force of attraction between the shared pair of electrons with the positive nuclei, okay? That's basically what electrostatic forces of attraction is. These two evidences, properties of giant atomic structures. The properties of giant atomic structures are that they are a few of the properties of the giant atomic structures are they have a high melting temperature, a high boiling temperature, and essentially the giant atomic structures have many uh, multiple, how do you call this? Multiple atoms or molecules mixed together. So let's just write this in detail. So if we are to have a giant atomic structure, it should look like this. Let me just get the exact diagram. Yeah, so let's look at the giant atomic structure of diamond. Diamond has a giant atomic structure, okay? It looks something like this. So each carbon is bonded to four other carbons. And remember, each carbon is bonded to four other carbons, so it'll just look something like that. And essentially, it creates like a whole movement of these. Sorry. Yeah, so it creates a lot of these. And yeah, this is connected to multiple as well. You know, each of them is connected to, that's already four, sorry. Each of them is connected to four. So what do we mean by this? Each of these are in diamond are covalently bonded together, okay? Carbon atom 1 bonds with carbon atom 2 by sharing one pair of electrons. So it is two electrons in total. And this is throughout. So it's here, 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 here. It's everywhere. This causes extremely strong forces of attraction, and giant atomic structures tend to have a high uh, melting temperature and boiling temperature. They are also very hard. They they are crystalline structure. You know, those are a few of the properties, but these are some of these are all over stuff, so we will skip this. But why did I say most of them instead of all of them? It's because graphite is an exemption, okay? Graphite has a lower melting and boiling temperature compared to how much it would have been expected to have had. This is because they do have a different structure. There are layers between the graphite, so this is going to be one hexagonal layer, and it'll be bonded by van der Waals forces with the other hexagonal layer. That doesn't look hexagonal, but yeah, that's what it is. Electron density maps should look like something like this. You have two covalently bonded, like let's say O2. The electron density map will look something like this. So it'll be very dense. Let me just shade it actually for you. This region of denseness is the shared electrons, okay? So X. That's how that's two pairs of electrons in an oxygen molecule, okay? So we can just stick that. I don't know why it's on the lower thickness. Okay, be able to draw a dot and cross diagram to show electrons in covalent substances, including molecules with single double and triple bonds, species with dative covalent bonds, including AlCl6, okay, Al2Cl6. So let's start off with what they first asked, okay? Um, let's look at chlorine. Sorry. Let's look at Cl2, let's look at O2, and let's look at N2. Cl2 is basically Cl, Cl, Cl. You can draw the positive nuclei if you want, and then it shares one pair of electrons. So this will just be Cl, Cl. Remember, two electrons is just one bond. O2, on the other hand, is a bit different. I don't know why I drew it like that. It's going to be O, O, and they share two pairs of electrons. So two pairs of electrons will cause a double bond, so it'll be O, O, okay? By the way, this is to fill out the subshells, the outer subshells to make it stable. N2 will be like this. N2 is a bit more, so N, N, and then it'll have three pairs of electrons, so it'll be N, N, okay? So basically each pair represents one bond. Now, Al2, Cl6. What is Al2Cl6? What is the difference? So, this is how it looks like. Cl will be bonded to Al. Al will be bonded to Cl. Al will be bonded to Cl, and so on, okay? Let me just finish drawing this, and then I can demonstrate the exact difference here, okay? Now, we can see this, but what looks to be different in this case? We do know that there is aluminium. One second, guys. Okay, we do know that aluminium has I'm just trying to search something up related to this. Okay, now there is a difference here with this. Aluminium has 3 electrons in its outermost subshell, okay? However, it is this structure cannot happen like if you look at it like this, okay? Why can't it happen? It's because aluminium isn't able to share that many electrons. We just said aluminium has, sorry, I need to get better at drawing. Al, the first subshell, okay? Second subshell has 2 electrons. Wait, I just made a mistake. This is not the subshell. This is the nuclei, okay? This is the first subshell. It has 2 electrons. This is the second subshell. It has 8 electrons, okay? And the third subshell is basically gonna look like this. The third subshell has 3 electrons. But it's sharing photons here, which cannot happen. So that's where dative covalent bonding takes place. Chlorine is able to share 2 of its electrons in order to gain that extra, to fill up its subshell. What do you mean by this? If you look at this also, chlorine cannot do this. Why? Chlorine has 7 electrons in its outermost subshell, and to make 8, it needs to share 1 electron. But it is sharing 2, meaning its other molecule, in this case Al, will also share 1, 1, meaning 2. So if it shares 2 electrons here, 2 electrons here, it will remain with 6, and this will equate to 10, which is not possible. Okay? You can't have 10 electrons in the outermost subshell for chlorine. So instead, dative covalent bonding takes place. This Cl here and this Cl here will be different. It will datively bond with Al. What do you mean by datively? It means that the Cl will donate both of its electrons. So the shared electrons will look like this, but then on this side it'll be X, X. X is the chlorine electrons, and the dot is for the aluminium electrons. So here, same thing, X, X, X dot, X dot, X dot, okay? That's how it's going to look like. That's dative covalent bonding. It's when one species gives both the electrons, okay? Be able to describe different structures formed by giant lattices of carbon atoms, including graphite, diamond, graphene, and discuss the application of each. Understand the meaning of, okay, I shouldn't have skipped that. But graphite, carbon, and graphene. We just talked about this. Carbon is going to be like this. So each carbon bonds to four other carbons, like so. And essentially this creates a very strong structure, okay? And this goes on for a lot. There are no free electrons. Each carbon bonds to four carbons, meaning it shares four electrons, and the outermost subshell of carbon has four electrons, meaning all of the electrons will be used, so there'll be no free electrons, so it will not conduct electricity. It has strong bonds throughout, strong covalent, so it is very hard, and it has a high melting temperature and boiling temperature. Graphite on the other hand is made up of this. This is carbon atom, carbon atom, carbon atom, carbon atom. Essentially, it's going to look like that, okay? And each carbon is bonded to its other carbon, like this. This is bonded to that, like that, okay? What do we want to show here? Each carbon is bonded to three other carbons, meaning there is one free electron, meaning it can conduct electricity. It is not hard. In fact, it's used as a lubricant. Diamond is used for drilling tools because it is very strong. You know, you can drill through anything. Not anything, but you get the point. Graphene is not hard. These layers can slide, so it is very soft and can be used as a lubricant. It has a relatively low melting and boiling temperature because, you know, of this layer again. And graphene, I mean, compared to diamond, it has lower melting and boiling temperature. Also, now actually let's look at graphene. If you take one of these layers and you just separate it, you get what's known as graphene. Graphene is used in mobile phones, you know, mobile electronics and stuff like that, okay? That's essentially what graphene is. That's all you need to know for what graphene is. So remember, strong covalent bondings throughout, even here, but graphite has weak van der Waals forces, which are like these, and graphene just looks like this. It's just a single layer of graphite, so it's not, you know, it doesn't have weak van der Waals forces. Understand the term electronegativity. So, what do we define electronegativity as? Electronegativity is a property that describes the tendency of an atom or a functional group to attract electrons towards it, okay? So, uh, what we should know is that electronegativity increases as you go from left bottom to top right. If this is your periodic table, this is the direction of increase of electronegativity. Meaning as you go up, it'll increase, and as you go to the right, it'll increase, okay? Why is this? As you go to the right, the how do I say this? The nuclei will contain more and more protons compared to atoms on the same period, but it's towards the left. So here you'll gain more uh, more protons in the nuclei than an atom here. So yeah, if you have more protons, the nucleus will attract more, hence you will get a greater electronegativity, okay? Also, why does it increase as you go up? It's because the atom size becomes smaller as you go down, as you go up. So the electron will be more easier to attract like this than like this. Okay, so as you go down the group, electronegativity decreases because of increase in atomic radii. So you can just take that. Know that ionic and covalent bonding are the extremes of a continuum of bonding type, and be able to explain this in terms of electronegativity differences leading to bond polarity and bond in bonds and molecules, and to ionic bonding if the electronegativity is large enough. Ionic and covalent bonding are essentially they work like this. If you look at the electronegativity difference between two substances, let's say NaCl, your electronegativity should be greater than, if it's greater than 1.5, so if it's greater than 1.5, it will be a ionic bonding. Okay, bonding will take place. If the uh, electronegativity difference is less than 1.5, like in O2 or N2, it'll be covalent bonding that'll take place. Okay, that's basically what we need to know from there. Yeah, uh, be able to distinguish between polar bonds and polar molecules and predict whether or not a given molecule is likely to be polar. Polarity is given by the electronegativity difference, okay? If you look at H2O, you will have an O, you will have H and H. This will be delta positive, this will be delta positive, this will be delta negative. There is no symmetry here. If you cut it into half or in any sort of orientation, you will not get symmetry. So this is a polar molecule because the charges are differently set, okay? That's how you should remember it. There are different molecules, let's say X, and then let's have Y, 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 Y. And this is delta positive, delta positive, delta positive, delta positive, delta negative. This is a non-polar substance. Why? Because there is symmetry. You know, from different sides, it'll attract the exact same. It won't cause, there's no electronegativity imbalance in a certain place. Here, there is electronegativity imbalance. The top is more negative than the bottom. Here, there is no electronegativity imbalance, okay? This part has the same electronegativity as this part. And yeah, that's how we should look at it, okay? From which sides, if you cut it into like symmetry-wise, okay? Yeah, that's how you know if a molecule is likely to be polar. Look at symmetry and look at if there are a disproportionate amount of uh, charges. If the charges don't balance, that means that they are likely to be polar. In the next video, we'll be looking at shapes of molecules and metallic bonding in one video.